Hello and welcome back to a new video in my Cuda development programming series. This is the second video and today we're gonna have a bit of hands-on on Cuda. I'm gonna explain basic stuff on how GPU programming works with Cuda, but we are not gonna go into too much details with the theory. This will be left open for the next video. Alright, so that we don't see like 2 times only PowerPoint, like 40 minutes just presentation, we want to actually get started and get hands-on with Cuda. So this is the project that we have created last time. We have this device launch parameters and Cuda runtime and all that glory and the default stdio header. That may actually include IO stream because we are gonna go C++ here, and let's just start by outputting a simple text. And basically what I want to say is this is our first Cuda application. Just a nice little info so that everybody who runs our program knows that this was the first time we tinkered around with Cuda. So print some infos. Alright, so if I would launch this, you would see that we're gonna get some outputs. This is our first Cuda application. Alright, so default C++ is working, so no C here, this is full C++. Good. So the next thing that we want to do is we want to prepare a work set. So we want to prepare a work set that we can then use. Let's also see out this so that the people are knowing what's going on. So I'm gonna say preparing work set so that everybody knows what's going on. Done, finish. So this tells everybody work set is gonna be prepared. And the next thing that we're gonna do is actually prepare the work set. And we saw totally we're gonna do vector addition. So let's actually define a vector here. So we're going to define a struct vector, and this vector is just going to hold an x, y, z, w parameter. So just a normal vector. So default for component vector here. And what we want to do is we want to create 2 working sets of a vector. So we're going to have an array of vector sets. So we have the arrow vector A set array, and we have another one, the set B, and we're gonna combine these 2 sets. And let's also add some conversion here because we're gonna allocate them dynamically, because this is gonna cost some memory here. So we're gonna have a size of times whatever that we're gonna insert here. So size of vector times a count, a vector count. And let's define this count up here. So let's do a const size t working set underscore count. I mean, yes, it should be a macro if I caps this, but yeah. So let's take 265 times 40 times 1024 should be good for a starting vertex set. So I'm gonna create and allocate 2 of them, which of course needs to be freed. So free memory. So of course down here we need to free all of that glory that we have just allocated. And now what I want to do is I want to fill this. So I'm gonna have a for loop size ti I smaller the working set count I++, and what I want to do is I want to assign some random values to that vector. We're going to have normalized vectors, so we're going to have a maximum of 1. So what I'm going to probably do is I'm just going to assign all these values to 1.f float times 1 divided by, well, actually we need to divide this to like that to have it like that. We don't need the 1 in here, so we're gonna divide this by a count, by a special count that we're gonna get, and we're gonna get this from std rand, which is gonna be an integer, and we're just gonna modulo this with 200 so that we have 200 steps that we can use. So that we divide all random into a group of 200. And yeah, we are differencing a null pointer because we haven't checked this. So let's add an assert here. Though they have assert included, let's actually include random and assert, C assert. And we're gonna assert array vector A and array logical. And we're gonna assert B and we're gonna say malloc failed for working set. Alright. So this is our working set and we're just gonna assign some random values to that. So we're gonna have an X, Y, Z, W. Let's also CT random, of course. So let's do an srand, std time. It's just std time from null pointer. Yeah, there we go. So this gives us a random seed that's change every time, and I'm just gonna initialize stuff. And let's now duplicate all of these. And let's also initialize the B vector. So we now have initialization for A and B vector, and we have a nice and cute working set. So prepare working set. We are gonna also need a result array. So we need an array where all of our results are written to. I'm just gonna do this one as well here with the malloc. Now we basically have A, B, and result. So basically everything that we need, and we're gonna put this into the result. Alright, before, let's of course also free the result, and before we're gonna free everything, I'm gonna print some values from result. So I'm just gonna do a small little for loop, size ti 0, a smaller 5, e++, and I'm just gonna do a stdc out. Or actually, I might want to do a print f because it's a bit more straight. No, let's do a c out. Let's stay here with C++. But we're gonna do some IO madness. So what do we need to do? We need to say std set per. So we don't set this. We're gonna set an set w to 8. And fixed has no parameters, just like that. And we don't need any fill, or we might get some issues. So this should be how this should be what we want. We want to have this as a fixed point, like that. And then we should just be able to echo out the array vector result at position I. We're gonna have an X, and I also want to label this correctly. So we're gonna have X equals. We're gonna have top y equals, let's copy the full statement from here, so like that. So we have x, y, z, w, maybe put this into a new line so that it's a bit more pleasing to look at, and do a W here and an std end line like that, so that we can basically just see out a few elements. And I'm just gonna echo out the first ones, and then I'm gonna echo out some dots and an std end line. And I'm gonna copy this for loop again, and we're gonna show starting from working set count -6 smaller working set count, like that. And we're gonna echo out a few more of them. So this should now give us some random and invalid data, because we haven't initialized the result. So yeah, we are getting some issues, but we can at least see that the format is what we want. And we have a, I'm an idiot, it must be -5. Let's see. Again, we should get some random values, or basically not random. This is again this value to what Microsoft is initializing each malloc call when it gets allocated. But at least we have like a proper display here. Right, I don't care. It's looking good, so I don't care. All right, so now we the only thing left to do is we need to actually process the data. That's the last thing that we need to do. And we're going to start by processing the data on the CPU. So I'm going to write a nice little void that is going to be called, I'm going to call this CPU vector array add, which is going to take a const vector pointer array A, and it's going to take another const vector pointer array B, and it's going to take a vector pointer array result, and it's gonna take a size t count. And what's this gonna do? It's gonna have a nice little for loop from I is equals 0 to count I++, and what I'm gonna do in this for loop, well, you guessed it, array result at position I is equal to array A at position I plus array B at position I. But we can't do this because arrays don't have this operation defined, or not arrays, but vectors have this not defined. We need to do the component wise. X, Y, Z, W, W, Z, Y, X, Y, Z, X, Y, Z, W, like that. So now we have our nice CPU function, or let's just call it kernel. CPU vector addition kernel. We're gonna state this terminology because the terminology of the GPU programs is kernel, and by keeping this kernel as well, we can easily like see what it is. Alright, so we have a kernel that's going on here. So now we just need to call it basically. We need to call CPU vector add, and before we're gonna do this, let's do an stdc out computing result. And then std end line here, and then we're gonna just call this function with the arrow vec A, the arrow vec B, and the arrow vec result, like that. And we need the count, of course, as well, which is the working set count. There we go. If I would now execute this application, you're gonna see after it builds. Preparing work set, computing results, and we are getting some values that are no longer looking ugly. I think. Yeah, they are looking good. And now the width is also matching. Now we have the chars that I'm looking for, the 8 chars here. So, or is it matching? I don't care, but basically we have a uniform format. That's what I want to say. Alright, so we have some values. I cannot tell you if they are good or bad, but they are good because, well, what should go wrong here? We're gonna see if things are actually going to plan later on in the series when we do like proper work, but for now we just assert that the GPU has computed this properly, and I don't want it to close even though I right-clicked on that. So yeah, everything going to plan. Now let's move this to the GPU. How can we do this on the GPU? It is actually not that hard. We can write a little function, same signature as the other one. Void GPU vector array add, in this case not CPU but GPU, and we're gonna add in the same thing that we added before. The only thing that we're gonna omit is the count, and we are also gonna do the same thing, but only thing that we have is that the index is no longer defined, so we need to somehow define it. I equals 0. Just gonna put this as 0 for now, so do computations like that, and here we're gonna do calculate index. So what is the difference between the GPU and the CPU? On the CPU we wrote a for loop that basically was executed by our application. So basically our application in one single thread we looped count times. So in this case 265 times 1024 times we have looped through this what is in here. Now the GPU works differently. As I already told you, the GPU has many cores and thus can run many threads. And basically what we're gonna do is we're gonna write a function that is being called by this GPU thread. So we are not allowed to loop in here, or we can loop in here, but it would be nonsense, because if we would loop in any in every of these programs, we would overwrite our own data. So we would then like 265 times 1024 do the same computation. But that's not what we want. So basically what we are defining is kind of like a thread entry point called GPU vector array add that is being called by a thread, by a GPU thread. And as soon as this GPU thread is called, we kind of like need to find the index of the current thread. And when we have the index of the current thread, we can do our computations. It is not actually that straightforward to get this. There is something that we can do to get this. There are so-called built-in members on Cuda. So, whoa, what happened here? I have just added some comments that help you better understand how the GPU works. We're gonna go into all of that madness in the next video in full detail. So I just wanna rush over this so that you can understand what I'm gonna write. Alright, so we are currently looking at a thread. So this function is executed by the thread, and from the metadata that we have for that current thread, we want to compute which element of the array we need to take to compute it, assuming that each thread does one vector addition. Alright, so we have something that is called thread index. That is basically the index of the current thread. This index has a dimension, a three-dimensional dimension of x, y, and z. Since we are doing a linear operation, we're just gonna do an x. This has nothing to do with 3D rendering or anything. This is just some terminology that help us to better decide which indices we can decide. So if we want to, this is just logical thing. This three-dimensional stuff is just logical. Since we are not thinking three-dimensional, we have a plain array, not an image or a three-dimensional world or whatever. We're just gonna take a look at this two-dimensional with just the x coordinate. So we have an x coordinate of a thread. Now you would think, alright, if it is one-dimensional, good, you are good. You can just take the index of the thread, and then you have your index to the total working set. This is, however, not true, because there is a limit of threads that can run. Basically, the GPU has a limit on how many threads it's executing parallel, so simultaneously, and at some point the GPU needs to make a cut, and this is why it is a bit different organized. So the thread index is basically from a current working group that is running on the GPU. Just a collection of threads that is running on the GPU. And what we want to do, basically, is we want to take this local index, which is for the current group, and we want to add this to the index of the full group that is currently running. And the group that is been running is called a block. So we also have a block index, and still one-dimensional, so we have a block index.x. This block index, however, is just incrementing always by 1. So it's not incrementing by like how many threads per block are running. It's only incrementing once 1 per block. So we need to multiply the index of the current block, the current working group, by the kind of like dimension of a block. The x dimension of a block. And as you would expect, block dim stands for block dimension. So the current index of the block multiplied by how many threads per block we can execute gives us kind of like a per block index, which then needs to be added to the local thread index, which is per block, to give us a normal index I. In reality, it's a bit more complex, but it is like that. So we have like threads that are organized in blocks that are organized in a grid, but we're gonna cover all that stuff in the next video. So for now we are just doing a simple computation of the index like that, and then we're gonna do our computations on that index. This might seem a bit strange first to admit, because it is not straightforward. It is quite not hard, but it is challenging to understand, but it's okay for now. Alright, so now let's rewrite this code here that we had with the CPU vector add, array add, to the computation on how we would do this on the GPU. So presumably we just call the GPU vector array add. So we would input an array add A, error vector A, and error vector B, and the arrow vector R for result. So back like that. So basically this would just how to call it, but basically that doesn't work like that because it's a Cuda program. And to make it a Cuda program, we use these triples, greater than, smaller than signs, and this basically tells the Cuda compiler, hey, this function should be executed but on the GPU. But to actually make this a valid function for the GPU, we need to define it a bit different. So by now, it's just a normal C++ function. We, however, need to kind of like expose this to the Cuda compiler. We can do this by adding this global flag. This global flag basically tells the C++ compiler to kind of like put this in the right state so that later on the Cuda runtime can kind of like analyze this function, or however the Cuda runtime works. We don't care how the Cuda runtime works. The Cuda runtime just needs this flag here before the void. And this makes this function now Cuda callable. And also these members are now valid. Right? Good. Now, basically, this executes this on the GPU, but we need some parameters inside these brackets. It's like template parameters, but not template parameters. And basically, we need to define in there how this is going to be launched. So we need to define how many blocks we want to run, and we need to find how many threads per block are executed. So basically, how this is populated. So basically, until which index our block index is going to go, and basically a size of a block. And to do this, we need to do some additional computations. So let's do this. We're going to have a size t block size. Let's make this const so that nobody tries to modify this. And let's just plainly set this to 265. There is a limit. I think on modern GPUs it's 1024. But for now, we're just going to say block size 265. Then we're going to define another const integer, which is going to be the block count. And basically, to get the block count, we're just going to take our full working set and divide it by the block size, which basically tells us how many blocks we need of that size to get all of our computations. And with these two parameters that we have just defined, we can now feed our nice little Cuda invoke. So the first thing that we want to have is we want to have a block count, and then we want to have the block size. Block size, like that. It's still red because IntelliSense thinks, what the fuck are you doing here? But we don't care what IntelliSense thinks because we know it's good. It works. It is okay. We can add this, and even though it's looking a bit bad, it works. So this is how you would call the GPU. But now comes the big issue. This memory that we are referencing lives on the CPU side. We need to copy this over to the GPU, sadly. So this is basically just our last step. This is our execute GPU kernel. What we need to do before is we need to allocate GPU memory, and we need to copy CPU to copy arrays to GPU. So this is all required before we can actually invoke this. But it is not that hard to allocate memory. Above here we had this malloc, and it's not that different to that. So let's get started by having a few vector pointers. So we're going to have a vector pointer, which is the GPU array vector A. And this is going to be starting at null pointer. And since I'm going to do this dirty and inline, let's do this like that. And let's copy this over like that. And let's create the array B and the array result like that. And now we have basically some memory pointers on the GPU that we can now reference in our function here, like that. So still, as you can see, there's something missing. We, of course, need to allocate memory. And how are we going to do this? Let's see. We want to say Cuda Malloc. As simple as that. Instead of malloc, Cuda Malloc. The signature is a bit different. The signature is pointer to pointer. So we insert the vector A pointer here. And we want to have a size, which is the size of vector times working set count, and boom, we have allocated. Let's we're gonna assert later on. Let's do this like that. So vector A, B, and result all the same. And then we're gonna just do a simple plan assert here. So everything of that needs to have a value. So like that, we see. How did I call this up here? Malloc failed for working set. Cuda Malloc failed for working set. So This is basically allocating memory on the GPU with Cuda, and do never try to use this point on the CPU. It looks like a legit CPU pointer, but it is not. It's just to be a bit more convenient, but it is not a CPU valid pointer. We can't just read from this. We always need to, if we Cuda Malloc this on the GPU, we cannot read from that. Important. Stop, asterisk, and never read or write to that. Good. So, what we alloc, we need to free. So, Cuda free, free, there we go. GPU, array vector A, B and result, make sure to free it as well, down here. Alright, next thing that we need to do, we need to mem copy over to the GPU. How can we do this? Well, you guessed it, instead of mem CPE, Cuda mem CPE. And what it's going to take is a destination, which is our GPU array vector A, a source, which is our array vector A, and a size times our working set count, which is the size of vector, times working set count, and we need a kind. This kind tells Cuda how to interpret these pointers. So by default, Cuda doesn't know which is a GPU pointer and which is a CPU pointer, or better to say, host for CPU pointer and device for GPU pointer. So we need to tell Cuda what this is. So Cuda mem copy. We want to copy from our host to the device. So host to device. Copy from host, which is our PC, to the device, the GPU. Like that. And we want to also do this with vector B. Here as well, and we could, this returns in Cuda error T, we could assert that this is good, but memcopy is not that crucial to succeed, so we're gonna leave this as that. Last thing what we need to do is, of course, we need to fetch our result, fetch result from GPU, and so we're gonna call another Cuda mem CPI, and now we are copying to our array vector result as a destination from our GPU vector result, size of vector again times working set count, and we wanna Cuda mem copy CPI device to host, so from our device back to our host. Oh, I write Cuda, Cuda like that. All right, there we go. And this should copy back our values. And looking at this should work. It's gonna be times slower. It's gonna be like 100 times slower than on the CPU side, because like that's not really something that you would do on the GPU, but it's a nice try out if everything is working. So let's press F5 and see what we get. Is everything gonna compile? I hope so. And ooh, we got something. So preparing workset, computing, and we get some values. And they all look random, and because they're looking random, they look good, I think. Yeah, definitely. They are a bit, yeah, but this is like random. If I would restart this, I closed the CMD. I hate it when I close the CMD, but yeah. We get different values if you restart, which already, oh, there we had an issue. We had some infinite here. Why ever we get some infinite, but it works. Probably because yeah, we divided by 0, which is going to give us some infinite there, of course. If we add 1 here, we gotta solve this issue with divided by 0, like that. Interesting that we haven't experienced that issue before. Ah, right. Now it's looking a bit better. But yeah, that's looking good, because now we are adding a full 1 to that. Yeah, of course, this needs to go inside of that. I was a bit confused what's going on there, but it must be like that, because if not, it's applying this after the division, which we don't want. So now we are good. Yeah, that is looking good. No infinite or stuff and all small values, because probably small is the random, and we're dividing 1.0 f, so yeah, it's looking good, it's looking good. So now we have basically written our first Cuda application. How can we verify that it runs on Cuda? How is it called? Insight systems Let's open Inside Systems. Yes, we can. GPUs row on top. Bam, amazing. Let's quickly build this in release because you should always profile something like that on release. So I'm gonna rebuild this. And I'm gonna select my desktop here inside of that. And now it's gonna start everything that it's gonna need. And after the profile has been initialized, we can select the command line that we need to execute, which means basically the app, which I'm going to need to find very quickly, which is on G, dev, CPP, GitHub projects, Cuda tutorial, binary, simple vector add release, simple vector add.c++, and we want to automatically profile everything, probably. And we want to make sure to collect the Cuda trace. And collect GPU memory usage. Yeah, let's do this. Right, so start. And computing results, done. It is waiting for something, is it? Whatever, stop. Stop profiling, good. And now it's gonna collect some samples and gonna analyze stuff. And there we go, our first report has been finished. And there we go. So, let's analyze what we got here. Let's make this a bit bigger at least, and now we can see what's going on. Let's expand this a bit. Alright. So, how are we gonna do this? We are gonna do this. This is all a bit... yeah, hard to see. So basically, first of all, we get several processes that were involved during this, this profiling. We just care about our simple vector add here with this process ID. And you can see that we had several stuff running. So we had some Windows, Microsoft Windows, DXG, kernel, whatever this is probably some driver thing. We had our Cuda hardware running here. And we also had some VDDM activity. So basically some driver activity for our GPU. So some queuing that was going on here, but I'm not going to go into too much detail here. What we basically care is that CUDA spike here, which we're gonna interested in. Can I zoom in, filter and zoom in? Is it the right way? Yeah. Or can I also like move that one? Yeah, I can also move that one. But basically what we have is we have some bit of memory usage here, so you can basically see that we had 4 megabyte of memory used, and then we had like it's still a bit. Let's zoom in, filter and zoom in. Let's go again, filter and zoom in. So basically these were our memory allocations. Probably I can just see that there's something going on here. Genau, yeah, of course. Yeah, you can see basically what's going on here. So basically this was probably a memory allocated CUDA, because it was also freed last. So this is our first malloc on CUDA, then it's the second CUDA malloc. So we can actually compare this. So let's open up a calculator instance. Where are you? There you are. So basically we had 1024 times 256 as the size of memory. Now on each of these vectors we had 4 floating point values, and floating point values are 32-bit. Divided by 8 we are at bytes. Now we can divide by 1024, so this basically means we are now at kilobyte. Now I can divide this by 1024 again, which means 4 megabyte per working set. So you can actually see this is correct. So the memory usage gone up here. So for 4 megabyte here. So this was our first CUDA malloc. Then there was our second CUDA malloc, which was now going up to 8 megabyte here. And then there was the third CUDA malloc, which went up to 12 megabyte. And actually see that the first malloc did take longer because it probably needed to initialize some kind of like dedicated memory for application. Probably, just suspecting anything. And basically the next thing that we have after here is we have a CUDA memory operation in progress. So this is basically our first CUDA mem copy. So we can see H2D, which means host to device. That's our first mem copy, which took 1.1 second here. Then we had our second CUDA mem copy, H2 device, host to device, next copy. Another second here. Why is it that high? It wasn't that high. The program was faster. I know why it's doing that. It's more like, yeah, like 125 milliseconds. And I think it's just a timestamp where it happened. Yeah, that's the time. It's not the time it has taken. It's the time where it happens. Yeah, it's the time where it happens. Can I select this? Then we can see kind of like, yeah, if I would select this, you can see that this is probably... It did take like 700 or up to 800 microseconds here. So this was basically our 2 copy operations to the GPU. Then we have the small little spike here. Let's zoom in here. Filter and zoom in. And then we had this small little spike here, which is basically our kernel that was running. So you can actually see, if I hover over that, you can see GPU vector array at begins, ends. You can see that there's some grid stuff and block stuff going on, launch type regular, and stuff that we currently don't know, but basically we care about the name GPU vector array at. So basically this was our kernel that was running on the GPU, and after that you can see we had this memcopy device to host. So basically this was the copy operation of copying the data back to our CPU. Can I zoom out a bit? Can I move these bounds? Nah, maybe not like that, but yeah. Now I'm completely lost. Zoom a bit. Wanna zoom out, zoom out, zoom out, zoom out. Alright, I'm here. Let's zoom in again. I wanna have this full operation. So actually, if you take a look at this, basically we had 8 milliseconds of full operation for this kernel that was running on the CPU. Sorry, for this operation that was running on the GPU. We took approximately the 7.2 milliseconds. But actually, the operation on the GPU that was actually being executed was just 18 microseconds. So all of our computations on the GPU, all this vector addition took 18 microseconds, but we had like a full-blowing amount of overhead copying data from and to the GPU. And this is basically the bottleneck that we need to overcome. Operation on the GPU does only pay out if the copy operations are smaller than the time it's going to need. So if all transferring plus the kernel on the CPU is smaller than the full operation on the GPU, like everything with copying to the GPU, copying, performing the operation on the GPU, loading data back from the GPU, all that must be smaller than the plain operation on the CPU, so that everything is going to plan. So you can see basically, well, that is actually all we do. And this is a very helpful tool. On this tool we can like see where we have bottlenecks, to where our copying is going on and all that stuff. So yeah, it's very nice to kind of like debug stuff and see if stuff is actually worth doing. All right, so this concludes our first hands-on video on Cuda. In the next video we're going to talk about what's all about these thread indexes, block indices, block dimensions, grid dimensions, all that stuff. We're going to talk about all that glory of GPU and what is the benefit and how do we actually group stuff together. We're going to talk all about this in the next video in a theoretical approach. So yeah, thank you for watching. We're going to see us in the next video. Make sure to like and subscribe, and I'm going to wish you a nice day. Bye.